In 2023, the James Webb Space Telescope pointed at empty darkness and found a massive galaxy blazing with billions of stars when the universe was barely 300 million years old. Far too young for something that complex to exist. This impossible galaxy isn't alone. Webb's discoveries are forcing scientists to ask an uncomfortable question. Have we fundamentally misunderstood how the universe works tonight? Let's explore what's really going on out there. Imagine you're a photographer. You set up your camera, point it at a completely empty patch of sky. No stars, no galaxies visible to the naked eye. Just darkness. And you leave the shutter open, not for seconds, not for minutes, for 5 full days. What would you expect to see? Maybe a few faint smudges, maybe scattered dots of light. Dim and distant. That's what astronomers expected when they pointed the James Webb Space Telescope at one such empty region in 2023. Instead, they got something impossible. Thousands of galaxies appeared. Spirals, ellipticals, irregular shapes. Galaxies everywhere, packed into a frame smaller than a grain of sand, held at arm's length. But one galaxy in particular made astronomers stop and stare, not because it was the brightest, not because it was the closest, but because, according to everything we know about physics, it shouldn't exist. Not yet. Anyway, this galaxy existed when the universe was incredibly young, not middle-aged, not adolescent. We're talking about the universe as an infant, just 300 million years old. To put that in perspective, if the universe's entire 8 billion year history was compressed into a human lifetime of 80 years, this galaxy existed when the universe was less than 2 years old. Now, you might think, okay, a galaxy in a young universe. What's the big deal? Here's the big deal. This galaxy was already massive. It contained billions of stars. Not hundreds, not thousands, but billions. It was over 600 light-years across. It had complex chemistry, with oxygen already present in its gas clouds. And the problem, the universe didn't have enough time to make it. It's like baking bread. The recipe says preheat your oven, mix the dough, let it rise for an hour, then bake for 45 minutes. Total time about 2 hours. But imagine you set your timer for just 10 minutes. Open the oven, and somehow, there's a perfectly baked loaf sitting there. Golden brown, fully risen, still warm. Physics says impossible. The photo says it happened. Or think of it this way. You walk into a nursery, a room full of 2-year-olds playing with blocks and toys. But in the corner, standing next to the toy boxes, is a skyscraper. Not a model, not a drawing, an actual 50-story building, complete with offices, elevators, plumbing, electricity. Just there, in the nursery, with the toddlers. That's what Webb found. A cosmic skyscraper in the universe's nursery. The lead astronomer on the Discovery team, Stefano Carniani, said it simply. It is stunning that the universe can make such a galaxy in only 300 million years. Stunning is putting it mildly. According to our models of how galaxies form, models built on decades of observations and solid physics, this galaxy had no business existing yet. But there it is, in the photograph, undeniable. Now, before we dive into why this breaks everything we thought we knew, we need to understand what makes the James Webb Space Telescope special. Because it's not just a bigger version of previous telescopes. It sees differently, and that difference is everything. Here's the thing about looking into deep space. You're not just looking far away. You're looking back in time. When you see a star 10 light-years away, you're seeing it as it was 10 years ago. Because that's how long its light took to reach you. When you see a galaxy a million light years away, you're seeing it as it was a million years ago. Light is a time machine. The farther you look, the farther back in time you see. But there's a catch. The universe is expanding. It has been since the Big Bang. And it's still expanding now. And when space itself expands, it stretches everything in it, including light. Think of light as a wave, rippling through space. As space expands, those waves get stretched out. Like pulling on a slinky, the wavelength gets longer. Visible light has short wavelengths. That's why we can see it. But stretch those wavelengths enough, and visible light becomes infrared light. Infrared is just heat. It's invisible to human eyes. And it's invisible to most telescopes. The Hubble Space Telescope, for all its achievements, was built to see visible light and a bit of ultraviolet. It's essentially a giant version of your eye. But Webb was built to see infrared, heat, not light. And that changes everything, because those distant galaxies, the ones from the universe's infancy, their light has been traveling for so long, through so much expanding space, that it's been stretched way past visible light. It's become infrared, heat signatures from the cosmic dawn. Hubble couldn't see them. Its eyes weren't built for it. But Webb can. Webb sees the universe's baby pictures not despite the expansion of space, but because of it. The expansion that stretches light into invisibility for Hubble makes it visible for Webb. Think of it like this. You're trying to see someone in a thick fog. With normal vision, visible light, you can't see through the fog. But if you had thermal vision, like those cameras that see body heat, you could pick out the warm shape of a person even when fog blocks the light. That's what Webb does for the cosmos. It sees the heat, the infrared glow, from galaxies obscured by the fog of cosmic expansion. So when Webb pointed at that empty patch of sky for 5 days, it wasn't just taking a longer exposure than Hubble could. It was seeing wavelengths Hubble couldn't detect at all. And in those wavelengths, the early universe lit up. That galaxy we talked about, the impossible one, astronomers gave it a name, Jade G14 It's not poetic, but it tells the story. JADE stands for the Survey Program, James Webb Advanced Deep Extragalactic Survey, and that number at the end, it indicates how far back in time we're looking. The higher the number, the earlier in the universe's history. This particular galaxy is currently the record holder, the most distant, and therefore the oldest galaxy ever confirmed. We're seeing it as it was just 300 million years after the Big Bang. Think about that. The light that formed this image left that galaxy 13.5 billion years ago. It's been traveling through space for longer than our planet has existed, longer than our sun has existed. It started its journey when the universe contained no solar systems, no rocky planets, no's. And now, after all that time, after all that distance, those ancient photons arrived at a mirror floating in space, 1.5 million kilometers from Earth. And we captured them. We saw what that galaxy looked like in the universe's infancy. But here's what keeps astronomers up at night. That galaxy shouldn't have been there. Not then, not that big, not that developed. See, we had a story about how the universe grew up, a timeline, a sequence of events, and this galaxy breaks that timeline, which means either our story is wrong, or something very strange is going on with the universe itself. To understand why this is such a crisis, you need to know what we expected to find. Before Webb launched, we had a story. It was a good story, supported by decades of observations and solid physics. It went like this. In the beginning, there was the Big Bang, not an explosion in space, but an explosion of space itself. Everything that exists, all the matter, all the energy, All the space erupted into being about 13.8 billion years ago. At first, the universe was unimaginably hot and dense. So hot that atoms couldn't even form, just a soup of particles. A plasma so thick that light couldn't travel through it. For the first 380,000 years, the universe was opaque. If you could somehow be there with eyes to see, you'd see nothing but bright, blinding fog in all directions. No stars yet, no galaxies, just hot, glowing chaos. Then, as the universe expanded and cooled, something magical happened. The temperature dropped enough for atoms to form. Protons captured electrons. Hydrogen and helium atoms condensed out of the plasma, and suddenly, light could travel freely. The fog cleared. The universe became transparent for the first time. This moment, when atoms formed and light could finally travel. This is what we call the cosmic microwave background. It's the afterglow of the Big Bang. The leftover heat from that moment of clearing. We can still detect it today. A faint microwave hum coming from every direction in space. It's the universe's baby picture. A snapshot from when it was just 380,000 years old. But even after the fog cleared, there were no stars yet, no light sources. The universe entered what astronomers call the dark ages. Just hydrogen and helium gas, slowly being pulled together by gravity into denser and denser clumps. Over time, millions of years, these clumps grew massive enough that their centers became hot and dense enough for nuclear fusion to ignite. The first stars turned on, maybe around 100 to 200 million years after the Big Bang. They were massive, bright, and short-lived. They burned through their fuel in a few million years and exploded as supernovae. Those explosions did something crucial. They scattered heavier elements, carbon, oxygen, iron, into the surrounding gas. See, the Big Bang only made hydrogen and helium. Everything heavier had to be forged in stars. So these first stars, when they died, enriched the universe with the raw materials for more complex chemistry. A second generation of stars formed from this enriched gas. Then, a third generation. Meanwhile, these stars were clustering together, pulled by gravity into groups, then larger groups, then eventually, galaxies. This process was supposed to be slow, gradual, like building a city. You start with a few houses, then streets, then neighborhoods, and eventually, after enough time and enough construction, you have a metropolis. Galaxies were supposed to form the same way, starting small, merging, growing over hundreds of millions of years. By the time the universe was 500 million years old, we expected to see some decent-sized galaxies. By a billion years, we expected to see many. But at 300 million years, we expected to see mostly small clumps, proto-galaxies, building blocks, not finished buildings. That was the story, the timeline, the universe as a patient gardener, slowly cultivating complexity from simple seeds. And then Webb looked at the universe at 300 million years, and instead of finding seeds, it found forests, not just one massive galaxy, hundreds of them. The survey that found that record-breaking galaxy also catalogued nearly 800,000 galaxies in total, spanning nearly all of cosmic time. And in the earliest epochs, those first few hundred million years, Webb found roughly 10 times more galaxies than Hubble's observations had predicted should be there. 10 times more. That's not a small discrepancy. That's not our model was slightly off. That's our model was fundamentally wrong about something important. Caitlin Casey, one of the lead scientists on a major Webb survey, put it bluntly, since the telescope turned on, we've been wondering, are these datasets breaking the cosmological model? Because the universe was producing too much light, too early. It had only about 400 million years to form something like 1 billion solar masses of stars. We just do not know how to make that happen. We don't know how to make that happen. Let that sink in. The universe did something that our physics says shouldn't be possible in that time frame. Think about human development. A baby is born. It takes months to learn to sit up, a year to walk, several years to talk in full sentences, over a decade to reach puberty, and roughly 2 decades to reach full physical maturity. There's a sequence, a timeline, and you can't skip steps. You don't see a 2-year-old with a PhD and a mortgage, but that's essentially what Webb found. A cosmic 2-year-old with a fully developed galaxy, complete with billions of stars and complex chemistry. And it's not just the speed, it's the complexity. That oxygen we mentioned earlier, oxygen doesn't form in the Big Bang. It has to be created in stars through nuclear fusion. But here's the catch. It takes multiple generations of stars to build up significant oxygen. The first generation of stars makes a little bit of carbon and oxygen when they die. The second generation, formed from gas enriched by the first generation's deaths, makes more. By the third or fourth generation, you start to see substantial amounts. And each generation takes millions of years to live and die. So, detecting oxygen in a galaxy at 300 million years means that galaxy has already gone through at least 2 or 3 generations of stars. It's already cycled through its stellar life cycle multiple times. In what should be cosmic infancy, this galaxy was already middle-aged. One of the astronomers, Jakob Helton, noted, despite being so young, the galaxy is already hard at work, creating the elements familiar to us on Earth. Hard at work is right. This galaxy apparently pulled an all-nighter, multiple all-nighters. It speedrun the process that should take billions of years. Now, you might be wondering, how do we know when this galaxy existed? How can we be so sure about its age? It comes down to that stretching of light we talked about. As the universe expands, it stretches light. The farther light travels through expanding space, the more it gets stretched. We can measure exactly how much the light has been stretched. Astronomers call this redshift, and that tells us how far away the source is. And since light travels at a fixed speed, distance equals time. Farther away means longer ago. For this particular galaxy, the light has been stretched by a factor of about 15. That corresponds to a distance of about 13. 5 billion light-years of travel time, which means we're seeing it as it was 13. 5 billion years ago, since the universe is 13, 8 billion years old. Simple subtraction tells us this galaxy existed just 300 million years after the Big Bang. But here's something mind-bending. That galaxy is no longer where we see it, because space has been expanding the entire time its light was traveling toward us. That galaxy is now much, much farther away. If we could somehow see where it is right now, in this very moment across the universe, it would be over 40 billion light-years away. But we can't see where it is now. We can only see where it was. We're always looking at the past. Every photon is a time capsule. Light from the sun takes 8 minutes to reach Earth. So we see the sun as it was 8 minutes ago. Light from the nearest star beyond the sun takes 4 years. So we see it as it was 4 years ago. Light from that distant galaxy took 5 billion years. So we see it as it was in the universe's infancy. This is why Webb is so extraordinary. It's not just a telescope, it's a time machine. By looking farther into space, it looks deeper into the past. And what it's seeing in that deep past is rewriting our understanding of cosmic history. The universe wasn't a patient gardener after all. It was something else. A rush, a burst, an explosion of complexity that our models can't yet explain. Something was different back then. Maybe the physics was different. Maybe dark matter behaved differently. Maybe there were processes we don't know about yet. Whatever it was, the universe found a way to build galaxies fast, impossibly fast, and we're only beginning to understand how. But the early galaxies are only part of the mystery. There's another problem, equally troubling, and it has to do with something much closer to home. It has to do with measuring the universe right now. In the present day, and this problem, too, refuses to go away. Imagine you want to measure your living room. Simple task. Right, you get a tape measure. Stretch it from one wall to the opposite wall and read the number. Let's say it's 20 feet. Done. But then, just to double check, you use a laser measure. You point it at the far wall, press the button, and it reads the distance using the time it takes for a laser pulse to bounce back. The readout says 22 feet. You blink. You check both tools. The tape measure is calibrated correctly. The laser measure has fresh batteries and was working fine yesterday. You measure again. Still 20 feet with the tape. Still 22 feet with the laser. Now you have a problem. Both tools are accurate. Both methods are valid, but they disagree, and the difference is too large to ignore. So what's going on? Is one of the tools broken? Or is something weird happening with your room? And this is the disturbing possibility. Is the concept of distance not quite what you thought it was? That's essentially where cosmology is right now. We have two ways to measure how fast the universe is expanding. Both methods are sophisticated, tested, and verified by multiple independent teams, and they give different answers. The expansion of the universe is described by something called the Hubble constant, named after Edwin Hubble, who first discovered that the universe was expanding back in the 1,920 seconds. The Hubble constant tells you how fast space itself is growing. Specifically, it tells you how much faster distant galaxies are moving away from us for every additional unit of distance. The number itself doesn't matter as much as what it represents the rate at which the universe is getting bigger. And if you know the expansion rate, you can calculate a lot of other important things, like the age of the universe, its size, and its ultimate fate. So, measuring the Hubble constant is crucial, and that's where the trouble starts. The first method looks at the universe's baby picture. That cosmic microwave background we mentioned earlier. The afterglow from 380,000 years after the Big Bang. Scientists can analyze the patterns in this ancient radiation with incredible precision. Tiny temperature variations, tiny density fluctuations, all encoded in microwaves coming from every direction in space. Using our best model of how the universe works, a model that includes dark matter, dark energy, and general relativity, we can take those patterns and calculate what the expansion rate should be today. It's like looking at a baby's photo and using growth charts to predict their adult height. The cosmic microwave background is the baby photo. Our cosmological model is the growth chart, and the prediction is about 67 kilometers per second per megaparsec. Don't worry about the units. Just remember the number 67. Now, the second method looks around us in the present-day universe. It builds what's called a cosmic distance ladder. Here's how it works. First, you measure distances to nearby stars using parallax, the same principle that makes your thumb seem to jump when you close one eye and open the other. By observing how stars shift position as Earth orbits the Sun, you can calculate their distances with high precision. Next, you find special stars called Cepheid variables. These stars pulse regularly, brightening and dimming like cosmic lighthouses. And there's a relationship between how fast they pulse and how intrinsically bright they are. So if you can see one of these stars in a nearby galaxy and you measure its pulse rate, you know how bright it actually is. Compare that to how bright it appears, and you can calculate how far away it is. Finally, you look for supernova explosions in those same galaxies. Specifically, type Ia supernovae, white dwarf stars that explode with a remarkably consistent brightness. If you know the distance to the galaxy from the Cepheid stars, you can calibrate how bright those supernovae really are. Then you can use supernovae in much more distant galaxies to measure their distances. This ladder of measurements, parallax to Cepheids to supernovae, lets you measure distances across vast stretches of the universe. And once you have distances, you can measure how fast those galaxies are moving away from us. Plot distance against speed, and the slope of that line is the Hubble constant. Using this method, the answer comes out to about 73 kilometers per second per megaparsec. Remember the number 73. So we have two numbers, 67 from the early universe method, 73 from the local universe method. And you might think, okay, that's pretty close. Maybe there's just some small uncertainty. But here's the thing, both measurements are extremely precise. The uncertainty on each is only about 1 kilometer per second per megaparsec, which means these measurements are saying the Hubble constant is 67, plus or minus an, or it's 73, plus or minus an. Those ranges don't overlap at all. They're separated by a gap of about 6, far more than either method's uncertainty. In statistical terms, this is what's called a 5 sigma discrepancy. That means there's only a 1 in a million chance this is just a random fluctuation. This is real. The two methods genuinely give different answers. This disagreement has a name. Astronomers call it the Hubble tension. Tension is a polite scientific word for crisis. David Gross, a Nobel Prize-winning physicist, attended a conference on this problem in 2019 and was asked whether this qualified as a tension or a problem. He responded, "We wouldn't call it a tension or a problem, but rather a crisis. A crisis because if both measurements are correct, then something is fundamentally wrong with our understanding of the universe." For years, some scientists held out hope. Maybe there's a subtle error in one of the methods. Maybe Hubble Space Telescope, which measured many of those Cepheid stars, had some systematic bias nobody caught. Maybe the images were slightly blurred, blending nearby stars together, throwing off the measurements. Maybe, enter James Webb, with its sharper vision and infrared capability. Webb could see those same Cepheid stars more clearly than Hubble ever could. The hope was that Webb would either confirm Hubble's measurements, proving the tension is real, or find an error and make the problem go away. In 2023 and 2024, Webb looked at the same galaxies Hubble studied. It measured the same Cepheid variables, but with better precision, and the verdict came in. Adam Rees, the leader of the team that discovered the universe's expansion, is accelerating. Work that won him a Nobel Prize analyzed Webb's data. His conclusion: we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. Combining Webb and Hubble gives us the best of both worlds. We find that the Hubble measurements remain reliable. Translation: Hubble was right. The local measurement of 73 is correct, which means the tension is real. The crisis is confirmed. Rees went further, with measurement errors negated. What remains is the real and exciting possibility we have misunderstood the universe. Exciting. That's a word choice worth noticing. Not terrifying, not devastating, exciting. Because this is how science advances. When your two best methods disagree, it means you're missing something. And whatever that missing piece is, it's going to teach you something profound. So what could explain this? Why would the early universe method and the local universe method give different answers? There are a few possibilities, each more unsettling than the last. Maybe our cosmological model, the one we use to go from the baby picture to the present-day expansion rate, is missing something, some ingredient we don't know about. Early dark energy, perhaps, or maybe the properties of dark matter are different than we think. Or maybe there are particles or fields that exist that we haven't discovered yet. Or maybe the expansion rate has changed over time in a way we didn't expect. The standard model says dark energy is constant, always the same strength, everywhere, throughout time. But what if it's not constant? What if it's varied over the universe's history? That could make the early universe prediction wrong while keeping the local measurements right. Or, and this is the wildest possibility, maybe something is different about our local region of the universe. Maybe we happen to live in an unusual pocket of space, where the expansion rate is different from the average. This seems unlikely, given how much of the sky we've surveyed, but it can't be ruled out entirely. Whatever the explanation, one thing is clear: the universe is not behaving exactly as our best model predicts. Something is missing from our understanding, and that missing piece is big enough to change the expansion rate by 10%. 10% of a number that determines the age, size, and fate of the entire cosmos. Think about what that means. Our model of the universe, the lambda CDM model, the one that fits the cosmic microwave background so beautifully, the one that predicts the large-scale structure of galaxies so well. This model is incomplete. Not wrong, necessarily, but incomplete. Like Newtonian gravity wasn't wrong. Just incomplete until Einstein added relativity. We're at a similar moment now. Our universe is showing us cracks in the foundation. 2 cracks. Actually, early galaxies forming too fast. Expansion rate measuring too high. Both cracks confirmed. Both real. Both demanding explanation. And so we find ourselves in an uncomfortable position. We've built this beautiful model of the cosmos, and it's worked brilliantly for decades. But now reality is diverging from the model. The universe is doing things our equations don't predict, and we don't know why. Daniel Skolnick, a cosmologist at Duke University, declared at a conference in January 2025, the Hubble tension is now a Hubble crisis. A crisis, the kind that topples paradigms, the kind that forces scientists to rethink fundamental assumptions, the kind that, historically, has led to revolutions in our understanding. We're living through one of those moments. We just don't know yet what the revolution will look like. Here's a humbling thought. Everything you can see, every star in the night sky, every galaxy in Webb's images, every planet, every speck of dust, every atom in your body, all of it, combined, makes up only about 5% of the universe. 5%. That's it. That's all the normal matter. Everything made of protons, neutrons, and electrons. Everything that can shine, reflect light, absorb light, or interact with light in any way. 5%. The other 95%, we call it dark. Not because it's literally black or shadowy, but because we can't see it. We don't even know what it is. We've given names to it. Dark matter and dark energy. But those names are just placeholders, labels for our ignorance. About 25% of the universe is dark matter. We know it exists because we can see its gravitational effects. Galaxies rotate faster than they should, based on their visible matter. Galaxy clusters hold together more strongly than the gravity of their stars, and gas can explain. And when we look at how the universe's structure formed, the cosmic web of galaxy filaments and voids. The patterns only make sense if there's far more matter than we can see. So there must be something there, something with mass, something that pulls gravitationally, but something that doesn't emit, absorb, or reflect light. Invisible matter, dark matter. We know it's there. We just don't know what it's made of. It could be exotic particles we haven't discovered yet. It could be primordial black holes. It could be something we haven't even imagined. We're still looking. And then there's dark energy. This is even stranger. About 70% of the universe is dark energy, something that pushes space apart, making the expansion of the universe accelerate. In 1998, Adam Rees and his colleagues discovered that the universe's expansion isn't slowing down. As everyone expected, it's speeding up. Galaxies are flying apart faster and faster. Something is driving that acceleration. Some kind of energy embedded in space itself, growing more dominant as the universe gets bigger. We call it dark energy, but we have no idea what it is. It's not matter. It's not radiation. It's something else entirely. A property of empty space, a new field pervading the cosmos. We don't know. It's one of the biggest mysteries in all of science. So when we try to understand the universe, we're working with only 5% of the full picture. It's like trying to understand a symphony when you can only hear one instrument out of every 20. You get some sense of the melody, maybe the rhythm, but you're missing most of the music. And this ties into our two mysteries, those early galaxies that formed too fast. Maybe dark matter behaved differently in the early universe, making it easier for gas to collapse into stars. The Hubble tension, maybe dark energy isn't constant. Maybe it's changed over time, making the expansion rate different now than it was in the past. Or maybe we're missing something even bigger. Maybe there's a component of the universe we don't even know to look for yet. Something that doesn't fit into our categories of matter. Dark matter, radiation, or dark energy. Something new. This has happened before. You know, scientists thinking they understood almost everything, only to have reality pull the rug out. In 1900, the British physicist Lord Kelvin famously said there was nothing new to be discovered in physics, just more and more precise measurements. Oh, there were two small puzzles. He admitted, two little clouds on the horizon. One had to do with how light interacted with matter. The other had to do with an experiment showing that light's speed seemed constant regardless of how you were moving. Two small clouds. Seemed like minor details, except those minor details turned out to require quantum mechanics and relativity. Two completely new frameworks that revolutionized our understanding of reality. Lord Kelvin's confident, near-complete physics was actually standing at the edge of an abyss of ignorance. We might be in a similar moment now. Two puzzles. Early galaxies too fast, expansion rate too high. Seem like they might just need tweaks to the model. Or they might be cracks, revealing something much deeper. We won't know until we know. But here's what's beautiful about this. Science isn't about accumulating certainties. It's about refining our ignorance. It's about figuring out better and better questions. Every time we discover we're wrong about something, we're making progress, because we're learning where the edge of our knowledge is. Adam Rees put it well. Nature is making us work harder to figure out what is going on and why. Nature as a teacher, setting problems just difficult enough to force us to think differently, to question our assumptions, to build better models, and the fact that we can detect these problems at all, that we can measure the universe precisely enough to notice that our model is off by 10%, that we can see galaxies from 300 million years after the Big Bang. This is extraordinary. We're apes who evolved to find food and avoid predators on the African savanna. Our brains were shaped by survival, not by understanding the cosmos. Yet, here we are, building telescopes that can see the universe's infancy, devising methods to measure the expansion of space itself, detecting the gravitational effects of invisible matter, understanding that the universe is not only stranger than we imagine, but stranger than we can imagine, and then imagining it anyway. Eugene Wigner, a physicist and mathematician, once wrote about the unreasonable effectiveness of mathematics in the natural sciences. He was puzzled by the fact that abstract mathematical concepts, invented by humans often for purely intellectual reasons, turn out to describe the physical universe with uncanny precision. Why should the universe obey mathematics at all? Why should it be comprehensible? Nobody knows. There's no reason it had to be this way. The universe could have been chaotic, patternless, immune to mathematical description. But it's not. Somehow, the cosmos follows rules, and somehow, our brains, products of that same cosmos, can figure out what those rules are. Not all the rules. Of course, we're still working on it, still finding the boundaries of our understanding, still bumping into mysteries like dark matter and dark energy and impossible early galaxies. But the fact that we've gotten this far, that we can measure the universe's expansion, trace its history back to fractions of a second after the Big Bang, predict the patterns in the cosmic microwave background, is almost miraculous. We're part of the universe trying to understand itself, a temporary arrangement of atoms, forged in stellar furnaces billions of years ago, now conscious, now curious, now looking outward and asking, where did we come from? How does this all work? What are we made of? And the universe, through observation and experiment, answers back. Sometimes the answers are what we expected. Often they're not. Sometimes the answer is your question was wrong. Try again. Sometimes the answer is you're not ready for this yet. Come back when you've learned more. And sometimes the answer is simply, isn't it wonderful that you can ask, let's talk about oxygen for a moment. Simple element. 8 protons, 8 neutrons, 8 electrons. You're breathing it right now. It makes up about 21% of Earth's atmosphere, about 65% of your body by mass. Vital stuff. But oxygen is rare in the universe. It wasn't created in the Big Bang, that only made hydrogen and helium with traces of lithium. Everything heavier had to be made later. In stars, here's how it works. Deep in the core of a massive star, hydrogen fuses into helium. That releases energy, which keeps the star shining. Eventually, the hydrogen runs out. The core contracts and heats up, and helium starts fusing into carbon. Then carbon fuses into oxygen. Then oxygen into neon. Neon into magnesium. And so on, building up heavier and heavier elements. When the star finally exhausts its fuel, it explodes as a supernova, scattering all those elements, carbon, oxygen, iron, and dozens more, into space. The next generation of stars forms from gas enriched by these ashes. Planets form from that enriched material. Life, eventually, uses those elements to build molecules, cells, organisms. Every oxygen atom in your lungs was forged in a star that died billions of years ago. Every carbon atom in your DNA, every iron atom in your blood, every calcium atom in your bones, all of them came from stellar furnaces. You are, quite literally, made of stardust. Carl Sagan famously said, "We are made of star stuff," but it's more than just a poetic idea. It's chemically true. The atoms in your body are ancient. They've been recycled through multiple generations of stars and planets. They were once part of a nebula, then a star, then a planetary disk, then maybe another star, then eventually the cloud that formed our sun and Earth Those atoms are roughly 8 billion years old. They've existed, in one form or another, since shortly after the Big Bang. You're not a separate entity observing the universe from the outside. You're a temporary pattern formed by the universe itself, a local arrangement of matter that happens to be conscious. And now, think about what you're doing. You, this temporary arrangement, are contemplating the universe's history. You're thinking about galaxies that existed 13 billion years ago. You're wondering about dark matter and dark energy. You're asking how you came to be. The universe is observing itself, through you, through every conscious mind that has ever looked up at the night sky and wondered. This is profound in a way that's easy to overlook. For most of cosmic history, the universe just happened. Stars formed, galaxies collided, black holes merged, but none of it meant anything. There was no one around to observe, to understand, to care. Then, on at least one planet, orbiting one ordinary star in one galaxy among billions, matter organized itself into life, and life, over billions of years of evolution, developed nervous systems, brains, consciousness, the ability to think, to remember, to imagine, to question, and now the universe, through those brains, can reflect on its own existence, can study its own history, can ask, why am I here? How did I come to be? Where am I going? That oxygen in that early galaxy. Java's guess, 14, 0, Shasan, 5 billion light-years away, was created in massive stars just a few 100 million years after the Big Bang. Those stars lived and died, enriching the galaxy's gas. Maybe planets formed, maybe life arose. We'll never know. But what we do know is this: the same process that made oxygen there made oxygen here. The same physics, the same nuclear reactions, the same stellar life cycles. There's a continuity, a connection. That distant galaxy and our Milky Way are part of the same cosmic story. Different chapters, maybe, separated by billions of years and billions of light years. But the same story nonetheless. And you're part of that story too. The atoms in your body connect you to those ancient stars. The light reaching your eyes from distant galaxies connects you to the universe's past. The questions in your mind connect you to every other conscious being who has ever looked up and wondered. Now, consider the timing. James Webb launched in December 2021. It began science operations in July 2022. Its design lifetime is about 10 years, though it might last longer with luck. Let's say 20 years. Optimistically, 20 years out of 13. 8 billion. That's 0.000000014% of the universe's age. You, with your 80-year lifespan, are around for maybe 0.0000006% of cosmic history. And those two windows of time, Webb's operation and your lifetime, happen to overlap. Pure chance. You could have been born a century earlier, before Webb, before Hubble, before we even knew galaxies existed beyond the Milky Way. You could be born a century from now, after Webb has gone silent, when its discoveries are just historical footnotes. But you're here now, alive during the era when humanity first saw the universe as an infant, alive during the years when we're discovering that our models are wrong. That reality is stranger than we thought. Kevin Heinlein, one of the astronomers working on the JD's survey, said, "We're in an incredible time in astronomy history. We're able to understand galaxies that are well beyond anything humans have ever found and see them in many different ways. An incredible time." Not hyperbole, literally true. This moment, these decades, This brief window of history, we're witnessing revelations that previous generations could only dream about. Your ancestors, 1,000 years ago, saw the same stars you see. But they didn't know they were looking at nuclear fusion. They didn't know those stars were light years away. They didn't know about galaxies, or the Big Bang, or the expansion of space. They had mythology, philosophy, wonder, but not this knowledge. Your descendants, 1,000 years from now, will know things you can't even conceive of. They'll have telescopes more powerful than Webb, theories more sophisticated than our current models. They'll look back at 2025 and think, how quaint. They were just discovering the early galaxies were too massive, but they won't have this moment, the moment of discovery, the shock of seeing something that shouldn't be there, the thrill of realizing that the universe is more complex than the textbooks said. You have that moment right now, and it's not just about the science. It's about perspective. It's about seeing your place in the grand scheme. You're not the center of the universe. No, but you're not insignificant either. You're a part of it, a piece of the cosmos that woke up and started asking questions. The scale is overwhelming. Yes, 93 billion light-years across, hundreds of billions of galaxies, trillions of stars, numbers that exceed comprehension. But here's the thing you comprehend enough. You can hold in your mind the idea of 8 billion years. You can imagine, even if you can't fully grasp, what a billion light-years means. You can understand the concept of dark matter even if you don't know what it's made of. Your mind evolved for survival, for finding food and mates and shelter. Can think about galaxies. That alone is extraordinary. Tomorrow, you'll wake up, you'll make breakfast, you'll go about your day, you'll deal with small concerns, immediate problems, daily routines, and that's fine. That's human. The cosmic perspective doesn't erase the human scale. It doesn't make your life meaningless. If anything, it does the opposite. It makes the ordinary miraculous, because every ordinary moment, every breath, every heartbeat, every thought is happening in this universe, this impossibly vast and ancient cosmos. And it's happening now, in this narrow sliver of time when consciousness exists to notice. You're not just alive, you're aware of being alive, and you're aware of being aware, and you're aware of being part of something vastly larger than yourself. That's not insignificance. That's wonder. Ben Johnson, another astronomer on the Webb team, said, "This amazing object shows that galaxy formation in the early universe is very rapid and intense. And JWST will allow us to find more of these galaxies. Perhaps when the universe was even younger. It is a marvelous opportunity to study how galaxies get started. How galaxies get started. But also, by extension, how we got started. Because galaxies are where stars form. Stars are where elements form. Elements are what planets and life and you are made of. Understanding galaxy formation is understanding your own deep history. Science is the universe's autobiography, and you're reading it. Not just reading, you're helping write it. In a small way, by caring about it, by wanting to understand, by being curious. That curiosity is part of the cosmos too. It evolved here, on this planet, in your lineage of life. It's as natural as gravity or electromagnetism. The universe became complex enough to wonder about itself. And that wondering is what's happening right now, in your mind, as you listen to these words. So rest easy in this. You're connected to the stars, to the galaxies, to the deep past and the distant future, to everyone who has ever looked up and felt awe, to everyone who will ever do the same. The universe is big. Yes, ancient, Yes, mysterious. Absolutely. But you're part of it. Not apart from it. Part of it. And that's enough. We began with an impossible photograph. A galaxy that shouldn't exist yet. We explored the measuring problem. 2 methods giving 2 answers. Neither willing to budge. We confronted the uncomfortable truth that 95% of the universe is invisible to us. And we recognized that we, ourselves, are the universe becoming aware of its own existence. Now we arrive at the question, what do we do with all this? What do we do when our best models don't quite work? When reality refuses to fit neatly into our equations? When the cosmos keeps surprising us, confounding us, reminding us how little we actually know? We accept mystery, not as failure, but as invitation. There's a tendency, when talking about science, to present it as a march toward complete understanding, as if every discovery brings us one step closer to the final theory. The ultimate answer, the end of questions. But that's not how it works. That's never been how it works. Every answer reveals new questions. Every solved mystery opens up deeper mysteries. The more we learn, the more we realize how much we don't know. It's fractal ignorance. Zoom in at any level, and there's always another layer of unknown beneath. And that's beautiful, really, because it means the universe is inexhaustible. It means there will always be something more to wonder about, something more to explore, something more to discover. It means we'll never run out of questions. The physicist Richard Feynman once said, "I think it's much more interesting to live not knowing than to have answers which might be wrong." He was talking about the deep questions. Why does the universe exist? What is consciousness? Is there meaning to it all? But it applies to the smaller questions too. How do galaxies form? What is dark matter? Why is the expansion rate what it is? We don't know, and we might not know for a long time. And that's okay. It's okay to not understand. It's okay to be confused. It's okay to look at the data and say, this doesn't make sense yet. That's not a weakness. That's honesty. That's where knowledge begins. Adam Rees said it well, with measurement errors negated. What remains is the real and exciting possibility we have misunderstood the universe. Notice that word again. Exciting, not embarrassing, not disappointing. Exciting. Because being wrong means you get to learn something new. It means reality is richer than your model. It means there's more to the story. And for someone who cares about understanding, for someone driven by curiosity, that's thrilling. Imagine if Webb had looked at the early universe and found exactly what we predicted. Small proto-galaxies, slowly merging, building up over billions of years, perfectly matching our models. That would be satisfying in a way. A confirmation, a pat on the back. But how much more interesting is what actually happened? Massive galaxies already formed, stars already burning, oxygen already present. The universe saying, you thought you had me figured out. Think again. I'm stranger than you thought. More creative, more surprising. Now try to explain me. That's the gift. Not answers. Challenge. An invitation to think deeper. Look closer. Question more carefully. And this is where humility comes in. Cosmic humility. The recognition that the universe doesn't owe us comprehensibility. It doesn't exist to make sense to human minds. It just exists, doing its thing, following its laws. And if we're lucky, if we're clever and persistent and humble enough to admit when we're wrong, we might figure out pieces of it, but we'll never figure out all of it. Not because we're not smart enough, though our intelligence has limits, but because there are fundamental limits to what can be known. Beyond the cosmic horizon, Sushuleo, 5 billion light-years away, in every direction, there are regions of space that are receding from us faster than light. Light from those regions will never reach us. Not because it's too faint, not because we don't have good enough telescopes, but because the expansion of space itself prevents it. Those regions are, in principle, forever unknowable to us. There might be entire galaxies, entire clusters, maybe entire universes beyond our horizon, whole domains of reality that we cannot observe. No matter how long we wait, no matter what technology we develop, the edge of the observable universe isn't a technological limit. It's a fundamental limit imposed by the finite speed of light and the finite age of the universe. And even within our observable bubble, there are things we can't know. We can't see inside black holes, at least not directly. We can't observe what happened before the cosmic microwave background, because the universe was opaque then. No information from earlier times can reach us. We can't know the exact position and momentum of a particle simultaneously. Thanks to quantum uncertainty, mystery isn't just what we haven't figured out yet. Mystery is baked into the structure of reality. Some things might be unknowable, not just unknown. And that's okay too, maybe even good, because if we could know everything, if the universe were fully transparent to our intellect, what would be left? What would drive us forward? What would inspire that sense of awe? The philosopher Ludwig Wittgenstein wrote, "Whereof one cannot speak, thereof one must be silent." He meant that for questions beyond the reach of logic and language, we should stop trying to force answers and simply accept the silence. But maybe there's another way to look at it. Maybe silence isn't empty. Maybe it's full of possibility, full of the unspoken, the undiscovered, the yet to be imagined. Maybe the unknown is not a void to be filled, but a space to be appreciated. You don't have to understand everything to appreciate it. You can stand at the edge of the ocean without knowing the depth of every trench. You can look at a forest without identifying every species of moss. You can listen to a symphony without knowing how to read sheet music. Understanding enriches appreciation. Yes, but appreciation doesn't require complete understanding. Sometimes, mystery itself is the thing to appreciate. James Webb showed us that the universe is larger than we knew, older seeming than we expected, more complex than our models predicted. And our response doesn't have to be frustration. It can be wonder. Oh, we can say, it's even bigger than I thought, even stranger, even more surprising. How wonderful. Stefano Carniani's word comes back stunning, not troubling, not problematic, stunning, a word that means both shocking and beautiful. The universe stuns us, knocks us off balance, reminds us we're small. And in that reminder, there's something oddly comforting, because if we were big, if we were the center, the pinnacle, the point of it all, that would be a tremendous burden. But we're not. We're small, we're brief, we're a flicker of awareness in cosmic night. And that means we don't have to carry the weight of cosmic significance. We can just be, observe, wonder, appreciate. Tomorrow, you'll wake up, the sun will rise, as it has for billions of years before you were born, and as it will for billions of years after you're gone. You'll make coffee, maybe. You'll check the weather. You'll deal with whatever small concerns and large problems your life contains. And none of that is diminished by cosmic scale. Your joys are still real. Your sorrows are still real. Your relationships, your work, your moments of beauty and connection, all real, all meaningful, not despite the vastness of the universe. But within it, the cosmic perspective doesn't erase the human scale. It contextualizes it. It reminds you that this life, this moment, this breath is happening in the midst of something vast and ancient and ongoing. You're not outside the universe looking in. You're inside it, part of the flow, part of the story, and the story continues. Webb is still observing. Astronomers are still analyzing data. Theorists are still building models, testing ideas, trying to reconcile those early galaxies with our understanding of physics, trying to explain the Hubble tension, trying to figure out what dark matter and dark energy actually are. They don't have the answers yet. They might not have them for decades, but they're working on it. And someday, maybe, those answers will come, or new questions will replace them, or both. Either way, the universe will still be here. Vast, ancient, mysterious, waiting to be explored by the next generation, and the next, and the next. And you're here now, in this moment, aware of the mystery, touched by the wonder, part of the ongoing story of cosmic self-discovery. That's enough. It's more than enough. It's everything. Let these thoughts settle now. Let them drift. Like dust motes in sunlight. You don't have to hold on to them tightly. Just let them be. That galaxy, Jadis, Gis Kators, Zero. Its stars burned 13 billion years ago, long before our sun existed, long before Earth formed. Perhaps there were planets around those stars. Perhaps life. Perhaps someone, somewhere in that galaxy, looked up at their sky and wondered if they were alone. Their light traveled to us, across unimaginable distance, through expanding space, for longer than our world has existed. And now it's here. You saw it, or rather, you saw its memory, its echo, its ancient glow. They never saw ours. Those stars, if they still exist, if anyone is there, they're seeing the Milky Way as it was 13 billion years ago. Before our sun, before us, they see our past, just as we see theirs. Ships passing in cosmic night, separated by distance and time so vast that connection seems impossible. And yet, the connection is there. Light bridging the gap, understanding bridging the gap. You, here, now, aware of them. There, then, that's connection. Thin, perhaps, tenuous, but real. And there are hundreds of billions of galaxies, each with hundreds of billions of stars. Each star, potentially, with planets. Some of those planets, surely, with life, some of that life, maybe, with consciousness, with awareness, with the ability to look up and wonder. You're not alone, even if you never meet them, even if you can never know for certain. The universe is too big, too old, too full of possibility for Earth to be the only place where matter woke up and started asking questions. Somewhere, maybe, someone else is looking at their sky tonight, seeing our galaxy, or galaxies like ours, wondering the same things, feeling the same awe. You're part of a community you'll never meet, a fellowship of wanderers, scattered across space and time, bound together by curiosity, by that shared impulse to look up and ask why, how, what does it mean. The questions don't need answers to be worth asking. Sometimes, the asking itself is enough. You're lying down now, in bed, maybe, in a room, in a building, on a planet, orbiting a star, in a galaxy, in an observable universe 93 billion light-years across, in, maybe, something even larger beyond that, infinite space, finite but unbounded, multiverse. No one knows, but right here, right now, in this small space pillow, blanket, breath, that's enough. The cosmos doesn't demand you understand it, only that you exist within it. And you do. Your breath moves in and out. Automatic. Your body knows what to do. Your heart beats without instruction. Your cells divide and repair and function. You're a living process, not a static thing, always changing, always flowing. Part of the universe's ongoing creativity. The atoms in your body will outlive you. They'll return to the cycle. Earth, dust, air, water, eventually, perhaps, other life, other forms. The matter that makes you is borrowed, temporarily arranged into this pattern called you. And when the pattern dissolves, the matter continues, recycling through the cosmos, eternal. In its way, you are not permanent, but you are real. And while you're here, you get to experience this, the universe, through your eyes, through your thoughts, through your wonder. That's not insignificance. That's privilege. Mysteries remain. They always will. The Hubble tension, unsolved. The early galaxies, unexplained. Dark matter, unknown. Dark energy, undefined. And beyond those mysteries, deeper ones, why does the universe exist at all? Why is there something rather than nothing? Why does it have these particular laws, these particular constants? Why does it allow life, consciousness, awareness? No answers to those. Maybe there never will be. Maybe the questions themselves are wrongly formed. Maybe reality is too strange for human concepts to capture. And that's okay. It's not your job to solve cosmic mysteries tonight. Smarter people with bigger telescopes are working on it. Your job, right now, is simpler. Rest. Let go. The stars are still shining. Whether you're watching or not, the galaxies are still spinning. Space is still expanding. The universe is doing its thing, as it has for 8 billion years, as it will for billions or trillions more. And tomorrow, the sun will rise. You'll wake. You'll return to your life, your concerns, your small slice of space and time. And that's beautiful too, because the cosmic and the personal aren't separate. They're nested. You contain the cosmos, stardust, ancient atoms, and the cosmos contains you. Both are true. You're vast. You're tiny. You matter. You're temporary. You're connected to everything. You're utterly unique. Hold those contradictions gently. Don't force them to resolve. They don't need to. Reality doesn't have to make sense in human terms. It just is. And you're part of it. James Webb just uncovered the true scale of the universe. Turns out, it's bigger than we knew, stranger than we imagined, more mysterious than we can fully grasp. And you, this brief flicker of consciousness, got to witness the revelation, got to see the photographs, got to feel the wonder. Not everyone gets that. Not every moment in history has these tools. These images, these discoveries. You're here now, in this narrow window, aware of what we've learned, aware of what we don't know, aware that the journey continues. Let that be enough. Let the wonder settle into your bones, into your rest. You don't have to understand everything. You don't have to solve anything. You just have to be here. And you are. The universe is vast. You are small. The universe is ancient. You are brief. The universe is mysterious. You are curious. And in that curiosity, in that capacity to wonder, to question, to stand in awe before infinity, you touch something eternal. Numbers dissolve now. Facts fade into feeling. The distance, the time, the complexity, let it all blur into one simple truth. You're part of this, part of the cosmos, part of the story, a thread in the vast tapestry, brief, but woven in, real, here, now. Sleep well, rest easy. The universe will still be here in the morning, still vast, still mysterious, still beautiful, and so will you. Good night.